guys, welcome back to another round of chemistry notes. In this video, we're going to talk about moles, just like we did earlier this year, but now we're going to talk about them a little bit more in depth. So remember, a mole is just a word that represents a number. And again, this is something that you have encountered many times in your life, I'm sure. For example, a pair of shoes is 2 shoes. So the word pair just means 2. Or if you have 1 dozen cookies, that's the same as having 12 cookies. So the word dozen just means 12. You can use them interchangeably. Just like those, if you have 1 mole of particles, it means you have 6.02 times 10 to the 23rd particles. You can use those two interchangeably, mole or 6.02 times 10 to the 23rd. And remember, this number represents Avogadro's number. So the first time we covered moles, we really only talked about atoms. And atoms, or an atom, represents one single element. So it's an atom of sodium or an atom of carbon. Just one single element from your table. But we can also use moles to talk about different types of particles. So since the first time we talked about moles, we've learned about ions, which are charged elements like Na+, or a charged group of elements like nitrate, NO3-. Those are both ions, those are both particles. We've also learned recently about molecules. Molecules are the particles of covalent compounds, so things like water or glucose. Those are molecules, they are particles. We have a special type of molecule that we learned about a while back. There are 7 of this special type of molecule. These are your diatomic. Your diatomic molecules. So remember Brinkelhoff, which is bromine, iodine, nitrogen, chlorine, hydrogen, and oxygen, and fluorine. Even though these are technically each just one element, 2 atoms of bromine, 2 atoms of iodine, 2 atoms of nitrogen, it's more than one atom chemically bonded together. So that makes it a molecule. So H2O, C6H12O6, and any of your diatomic molecules. Those are all molecules, those are all types of particles. And last but not least, we have ionic compounds, which are made up of formula units. And formula units can be things like NaCl, which is just table salt, or copper 2 nitrate. Anything that is made of a metal and a nonmetal, or one of your polyatomic ions, those are ionic compounds, those are formula units. So moving forward, you're going to be using Avogadro's number to talk about the type of particle in the problem. Maybe that'll still mean atoms, maybe it'll mean ions, maybe it'll mean molecules, maybe it will mean formula units. You're just going to have to decide based on the problem what Avogadro's number really means, or what it can be applied to, because it will always mean 1 mole. Doesn't matter what you are talking about, but 1 mole of anything is 6.02 times 10 to the 23rd of that thing, always and forever. So you remember your mole math, we had some simple steps that we followed every time. You should start with what you know, multiply by a fraction. What goes up must come down. And when the units in the top of your last fraction are the units that you are looking for, it's time to do your math. And remember, when you're filling in your fractions, anytime you fill in a mole, it will be 1 mole. Anytime you're filling in a number of grams, it will be the molar mass, number of grams. Sometimes you'll have to calculate that, like when it's a compound, you'll have to add up all of the atoms to find your molar mass. And when you're talking about particles, you're going to use Avogadro's number. But again, particles can mean atoms, right? It used to mean atoms and it could still mean atoms, but now it might also mean molecules if you're starting with a covalent compound, or it could mean formula units if you're starting with an ionic compound. It's just going to depend based on the problem how you use this number. One last thing before we jump into our examples. When you are working with compounds, like we just said, this is one topic that people tend to get a little confused about in this unit. When you are working with compounds, water, sodium chloride, any molecule, any formula unit, Avogadro's number is not describing the number of atoms in that compound. It's describing the number of molecules or formula units in 1 mole. So if you are starting with a compound, if you're starting with something made of lots of atoms and you're trying to find a number of atoms, you're going to have to go 1 step farther. And it's not a difficult step. It's a pretty intuitive step. So let's say, for example, you have a flask filled with water molecules. And these water molecules, they pretty much look like Mickey Mouse heads. You've got your large oxygen in the center with your 2 hydrogens on the outside, because remember, water is H2O. So that means that we have 2 hydrogens and 1 oxygen to every molecule. So for example, in this particular flask, we have 4 water molecules. 4 molecules of H2O. So in this particular instance, we can just count them. It's easy to count them up, 1, 2, 3, 4. But maybe you've been working a problem where you started with a number of grams and you had to convert those grams to moles by putting grams on the bottom and moles on top. And then you multiplied again and put moles on the bottom and put molecules on top. We're talking about water, and this is where you would use your 6.02 times 10 to the 23rd with molecules, because we're talking about water. If you wanted to find the number specifically of hydrogen atoms, instead of just the particle, instead of just the molecule, to find the atoms, you'll have to go 1 step farther. And it's a pretty easy step. Are you ready? You take the number of molecules that you know. We know we have 4 molecules, and you will multiply it by a fraction. What goes up must come down. We'll put molecules of water in the bottom, and we will put atoms of hydrogen on top. So in every 1 molecule of water, there are 2 atoms of hydrogen. You can see that from the formula. H2O means that for every 1 molecule, there are 2 atoms, specifically of hydrogen. So then 4 molecules times 2 over 1 gives us 8 atoms of hydrogen. And you are probably thinking, yes, Miss Childs, of course, we get it. We could have just counted them, 1, 2, 3, 4, 5, 6, 7, 8. But that's for, 4 molecules. And if you had a mole of molecules, if you had 6.02 times 10 to the 23rd molecules of water, and you tried to count every single hydrogen atom, you would die of old age first. The universe would die of old age before you finished counting all of those hydrogen atoms. So you need to get comfortable with this step of, for every 1 molecule, there are 2 atoms of hydrogen. And this is one way to work these problems. Work it just like normal, grams to moles to particles, and then take it one step farther to find atoms. But there is another way you can do this. They get you to the exact same place, these two methods, and it's really just how does your brain like to do it better? So if we had a similar situation, but say we were starting with 6 moles of water, and we wanted to know how many hydrogen atoms that was. We can convert our moles of water to molecules of water to hydrogen atoms like we just saw, but we can also use this same 1 molecule of water is equal to 2 atoms of hydrogen. We can keep using this same ratio because if 1 molecule of water is 2 atoms of hydrogen, then in 1 pair of waters, this is really good grammar we're about to use, in 1 pair of waters there are 2 pairs, oh my, of hydrogen. And in 1 dozen waters, there are 2 dozen hydrogens. Maybe you've already seen where this is going. So we can say that in 1 mole of waters, there are 2 moles of hydrogen. It does not matter what units we are using. It's always going to be the same ratio of 1 water to 2 hydrogens, whatever we're doing. So we can actually do this conversion of water to hydrogen in the middle of the problem. And as we move forward in the year, this is where we're going to be putting this conversion more and more frequently. So it might be good to start getting used to it now. So for example, if I have 6 moles of water, I can multiply by a fraction. What goes up must come down. So I'll put moles of water down here. And I can go straight from moles of water to moles of hydrogen. That's a conversion factor that I know. So I can put moles of hydrogen up here. And in every 1 mole of water, there are 2 moles of hydrogen. So I still have to convert one more time to find atoms, right? That's what I'm looking for, is atoms of hydrogen. I'll do times a fraction. What goes up must come down. Moles of hydrogen in the bottom, atoms of hydrogen in the top. And just like any other thing, in 1 mole of hydrogen atoms, there are 6.02 times 10 to the 23rd atoms of hydrogen. And I will complete this math just like normal. It's going to get you to the same place, regardless of whether you do it this way or you work it the other way of 6 moles of water times a fraction. If we were working this the old way, the way we first learned moles, then from 1 mole of water we would go to 6.02 times 10 to the 23rd molecules of water. And then times one more fraction. In 1 molecule of water, there are 2 atoms of hydrogen. This setup and this setup are going to get you the same number, the exact same number of hydrogen atoms, because they're the same mathematically. They both follow our dimensional analysis rules. Just know that throughout the year, we are going to be doing a lot of mole to mole conversions. So this is how I'm going to be working examples for the most part. But if you just can't make this work in your brain, you are more than welcome to do it this way. It's going to get you to the same place. Yes? Yes. Let's see some examples. All right, example number 1 says given 150.21 grams of nitrogen gas, how many molecules of nitrogen gas are in the provided sample? With any of these problems, really with any problem at all, probably the first thing we're going to need is the formula for the thing we are talking about. So remember, nitrogen gas is sort of a special thing. It's made entirely of nitrogen because there are no other chemical names there, but it's not just N, right? Because that would be too easy. Nitrogen is one of your diatomic molecules, so nitrogen gas is N2. So then to find how many molecules of nitrogen gas are in the sample, we will set this up like a regular conversion. Start with what you know, 150.21 grams of N2 times a fraction. What goes up must come down. Grams of N2 go in the bottom. Moles of N2 go on top. When it's moles and grams, it's always going to be 1 mole, but the number of grams we're going to have to find, because it's not just the mass of 1 nitrogen atom, it's the mass of 2 nitrogen atoms. So we will add up all of the masses of all of our atoms. In this case, we can multiply. 2 times the mass of nitrogen, which is 14.01, gives us 28.02 grams per mole for N2. So that means that for every 1 mole of N2, we have 28.02 grams. That'll give us moles, but we are looking for molecules. Quick note, please do not abbreviate molecules as MOL or MOLE, because that's a pretty surefire way to make sure you're gonna work the problem wrong and get the wrong answer. Moles is moles. So we have 1 mole of N2. We will multiply again by another fraction. What goes up must come down. Moles of N2 go on the bottom. Molecules of N2 will go on the top. And in every 1 mole of anything, there are 6.02 times 10 to the 23rd of that thing. Because again, the particle we are talking about is N2, which is a molecule. So in 1 mole of this particle, there are 6.02 times 10 to the 23rd of that particle. Plugging all of this into your calculator, you should get 3.2272 times 10 to the 24th molecules of N2. And we want to round it to these 5 significant figures because we started with 5 significant figures. So we've got 1, 2, 3, 4, 5. Remember, none of the other numbers in the problem matter because these are all conversion factors, and conversion factors don't affect your sig figs. So if we start with 5, we should end with 5. Your answer is 3.2272 times 10 to the 24th molecules of nitrogen gas, N2. Part B of this problem says, how many atoms of nitrogen is this? We have 2 options here. We can either start with our grams of N2 to moles of N2 to moles of nitrogen atoms to individual nitrogen atoms and rework a lot of what we have already done. Or we can use our answer from the last step. We can use this 3.2272 times 10 to the 24th molecules of N2, and then we only have to do one more step. So personally, I prefer that second option. You do you. You want to work it out again? Great, that's more practice. So we've got 3.2272 times 10 to the 24th molecules of N2. And as the formula implies, for every one molecule, there are 2 atoms. So we will take what is now our given, we will multiply it by a fraction. What goes up must come down. Molecules of N2 in the bottom. Atoms of nitrogen in the top. And for every one molecule of N2, there are 2 atoms of nitrogen. So we'll take our 3.2272 times 10 to the 24th, multiply it by 2, and if you plug that in correctly, you should get 6.4544 times 10 to the 24th atoms of nitrogen. And again, if you chose to work it the other way, starting over from grams and doing the moles to moles conversion in the middle, you should still end up in the same place because you should still be doing the exact same math. And one more time, we're rounding this to 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5 significant figures because conversion factors do not affect those. So there's your answer for part B. Here comes your next example. Number 2 says, what is the mass in grams of 2 moles of silicon dioxide? Again, let's go ahead and write our formula. Silicon is a nonmetal, and oxide comes from oxygen. That's a nonmetal. So the fact that these are 2 nonmetals means that this is a covalent compound, which means it's really easy to name. The fact that it says silicon out front without a prefix means there's just the one silicon. Remember, if there's just one of your first element, it doesn't get a prefix. Mono is a bad thing, so don't say it if you don't gotta say it. So we've got silicon, and then dioxide means we have oxygen, 2 of those, SiO2. So now that we've got our formula, we can set up our problem. We are looking for the mass in grams of 2.00 moles of SiO2. So we'll start with what we know, 2.00 moles of SiO2 times a fraction. What goes up must come down. We are looking for grams. We can go moles to grams. That is the thing we know how to do. So we'll put grams of SiO2 on top. We know it's going to be 1 mole. To find the number of grams, we'll need to do a little bit of work, right? We'll take the mass of silicon. We'll take the mass of 1 silicon, which is 28.09, and we will add 2 oxygens, and those are each 16.00. When you add those together, 28.09 plus 2 times 16, it will give you 60.09 grams per mole as your molar mass for silicon dioxide. So for every 1 mole of SiO2, whoops, that looks like an 11. For every 1 mole of SiO2, we have 60.09 grams of SiO2. So then 2.00 times 60.09, when you type that into your calculator, it'll give you 120.18. But remembering our sig figs, we started with 3, we need to end with 3. So we need to round this. If we round it to 120.1.2, that is 4 sig figs, so that's not right. And if we round it to 120, this is only 2 sig figs because the trailing 0 doesn't count, so that's not right. But if we round it to 120 and then just the decimal point, remember this decimal point means that the trailing 0 does count now. So we have 1, 2, 3 significant figures. We started with 1, 2, 3 significant figures. Conversion factors don't affect anything. So our answer is 120 grams of SiO2. Awesome. On to the next one. Number 3 says how many nitrate ions are found in a sample of 0.14 moles of gallium nitrate. Well, the fact that we're starting with gallium nitrate and ending with just the nitrate ions means this is one of our new type of mole problems. It's going to require an extra step. You can either save that step for the very end, or you can do it as a moles to moles step in the middle of the problem. However you want to do it, just make sure you are following all of your normal conversion factor rules. And just like always, before we start this problem, we need a formula. So we know that gallium is Ga, and it's a metal, right? If you look on your periodic table, it is to the left-hand side of your little stair step, and the column it's in tells us it will form a 3+ charge. So gallium is Ga 3+. That's our gallium ion. Nitrate is an NO3, so 3 oxygens and then 1 minus. This is one of your first 6 weeks ions. You should just know this one cold by now. So we have 3 positives from our gallium, and we have 1 negative from our nitrate. So that means that to make these cancel, we will need 3 of the nitrates and 1 of the galliums, because that'll give us 3 positives here, 3 negatives here. So to write that, we will write it Ga, and you can write the 1 or you can just leave it. The 1 is implied. And then NO3, but since we have 3 of those polyatomic ions, we will put it in parentheses and then put 1 more 3 to show that this thing right here we have 3 of. Because again, otherwise it looks like we have 1 nitrogen and then 33 oxygens, and that is not a thing. So gallium nitrate looks like this. Now we can go ahead and set up our problem. So we'll start with what we know, which is 0.14 moles of our gallium nitrate, GaNO3, 3, times a fraction. What goes up must come down. So we'll put moles of gallium nitrate in the bottom. And as far as what goes on the top, that is sort of your choice. You could go to formula units of gallium nitrate, and then you'll do 1 more fraction. In 1 formula unit, there are 3 nitrates. Personally, that is not my favorite method. So I'm going to go from moles of gallium nitrate to moles of nitrate ions. Looking at your formula, or right here, we said that for every 1 of this formula, we have 3 nitrate ions. So that means that 1 gallium nitrate contains 3 nitrate ions. Or 1 mole of gallium nitrate contains 3 moles of nitrate ions. We're not looking for moles of nitrate ions, we are looking for individual nitrate ions. So we'll need to go times 1 more fraction. What goes up must come down. Moles of nitrate go on the bottom. And individual ions of nitrate go on top. Just like anything else, in 1 mole of ions, we have 6.02 times 10 to the 23rd individual ions. So 0.14 times 3 over 1 times 6.02 times 10 to the 23rd over 1, assuming you plug that in correctly, you should get 2.5 times 10 to the 23rd ions of nitrate. And again, double check your sig figs. We started with 2. All we used for the rest of the problem were conversion factors. So this is our 2 sig figs that we should end with. 2.5 times 10 to the 23rd ions of nitrate. All right, a couple more examples before you'll have some practice to work on your own. Here comes number 4, says how many moles of ions are in a 2.0 mole sample of aluminum oxide? By now, hopefully you know the very first thing we need to do is write the formula. So aluminum is a metal. It's in fact in that same column as gallium. So we're going to have Al3 plus as our aluminum ion. Oxygen is a non-metal. And based on the family it is in, we know it'll form a 2 negative charge. So to make these cancel out, we are going to need 2 of the aluminums, and we're going to need 3 of the oxygens. So that means that our formula is Al2O3. Now that we know this, we can go ahead and set up our problem. Start with what you know. We are given 2.0 moles of aluminum oxide, Al2O3, times a fraction. What goes up must come down. Moles of Al2O3. And if you look at this problem, in this particular instance, there is one really good way to solve this problem and one method that will involve several extra steps. We are starting with moles of one thing and ending with moles of a different thing. So you can go to formula units of aluminum oxide, but then you'll have to go formula units to individual atoms, ions, and then individual ions back to moles of ions. And that's going to be a many-step problem. Or we can go from moles of aluminum oxide straight to moles of ions. You'll notice it doesn't specify types of ions. It doesn't say aluminum ions and it doesn't say oxide ions. It just says ions, as in all the ions together. So we can see from our formula of aluminum oxide that one formula unit of Al2O3 is made of 2 aluminum ions and 3 oxide ions. So that's a total of 5 ions. So if one formula unit is made of 5 ions, then 1 mole of aluminum oxide is made of 5 moles of ions because the ratio remains the same. So then we have 2.0 moles of aluminum oxide times 5 over 1, and your calculator is going to say 10. This is one of those times you have to be smarter than your calculator because 10 is not the right answer. 10 only has 1 sig fig. You started with 2 sig figs, and used a conversion factor, so you should be ending with 2 sig figs. Again, this is where you'll need that awkward decimal point to make that 0 count, because the decimal point makes the trailing 0 count. Now we have 2 significant figures. We started with 2 significant figures. This is our final answer. Give it some units. 10 moles of ions. All right, we have one more example, and it puts all of the steps together. We've sort of been doing different chunks of the same problem, moles to moles, grams to moles, moles to ions. We are going to do the whole thing now. Are you ready? You should be. Number 5 says how many sulfate ions are in 347 grams of aluminum sulfate? We're going to have to do the whole thing here, from grams through moles all the way to individual ions. But before we can do any of that, we need a formula. We are talking about aluminum sulfate. Aluminum is a metal. Sulfate is an ion. If you have a metal and a polyatomic ion together, it is guaranteed to be an ionic compound. So we should write the ions. Aluminum, as we've already seen, has a 3+ charge. Sulfate, you should know, is SO4, 2-. That's one of your first 6 weeks ions. So to make these charges cancel, we will need 2 aluminums and we will need 3 sulfates. So that means that the formula here is Al2 SO4, but since we need 3 of this polyatomic ion, we will put it in parentheses and then give it a 3. So now that we have our formula, we can get to work. Start with what you know, 347 grams of aluminum sulfate. Times a fraction. What goes up must come down. From grams, the only place you can get is moles. So we'll put moles of aluminum sulfate on top. To fill in a grams and moles conversion, you need the molar mass. When you add together 2 aluminums, which each have a mass of 26.98, plus 3 sulfurs, which each have a mass of 32.06, plus 12 oxygens, which each have a mass of 16. When you add that all together, you should get 342.12 grams. So we will say that for every 1 mole of aluminum sulfate, we have 342.12 grams. And then once again, times a fraction. What goes up must come down. So we can put moles of aluminum sulfate in the bottom. And here is where you have to make your choice. I prefer moles to moles, so I'm going to put moles of sulfate in the top. And again, looking at your formula, for every 1 aluminum sulfate, there are 3 sulfate ions. So that means for every 1 mole of aluminum sulfate, there are going to be 3 moles of sulfate ions. We are not looking for moles of ions, we are looking for individual sulfate ions. So we will do times another fraction. What goes up must come down. We'll put individual ions of sulfate on the top. And in any 1 mole of a thing, there are 6.02 times 10 to the 23rd of that thing. So then it's time to just plug it into the calculator very, very carefully. 347 divided by 342.12 times 3 times 6.02 times 10 to the 23rd. If you can plug that all in without making any mistakes, you should get 1.83 times 10 to the 24th ions of sulfate. And again, Double check your sig figs. We started with 1, 2, 3. All we did were a lot of conversion factors after that, so we should end with 1, 2, 3. So that is your final answer. And at this point, you have seen pretty much every type of problem you could see, or at least a really good jumping off point. So now in your book, you've got several practice problems. Go ahead and pause the video, work through those examples, and when you're ready to check your answers, unpause. All right, hopefully this is what you got for those 11 practice questions. Again, double check sig figs, double check units. Your answers should look exactly like my answers. So if you worked through these and you're feeling good, it's time to move on to the next video, or move on to your quest, or move on to your test review, whatever you're working on. If you are not feeling great about these, maybe watch through the examples one more time or head into tutorials, get a little bit of help. But either way, good luck and happy studying.